Good afternoon, everyone. Welcome to the Geotalk. I'm very happy when I meet friends and bump into friends in different parts of the world. And I'm very happy that today Marco Fiorentini could join us and come and visit Wits University. Marco is Professor of Economic Geology at University of Western Australia in Perth. He's been there for a very long time.
Despite the accent.
And he's been traveling throughout South Africa to show our beautiful geology of South Africa to a group of master students in economic geology. And I see that everybody's excited and impressed. And I'm very glad because maybe there is a way for them to come back. So Marco, thank you very much. And we are really looking forward to hear your talk about the metallogenic continuum of an Archean craton.
Thank you so much. Thank you, Linda. Thank you, Grant, for having us here. It's a pleasure to be here. Buongiorno. So exactly, after 25 years in Australia, this is my accent. And every day I'm asked if I'm enjoying my holiday in Perth. And I always say that I start like this because it's the truth. Anyway, I hope you can understand the accent now. Don't worry, I'm not going to talk about the Capval crater because I would be totally scared about this. So I'll take you for a ride on the other side of the Indian Ocean and tell you a little bit about a crater that is closer to home, at least for me. I'm a professor at the University of Western Australia, and I'm also the director of a newly established center funded by the Australian Research Council, known as the Center in Critical Resources for the Future. And I'll tell you a little bit more about that at the end of the talk, simply because I'm on a promotional tour of the center. So I take every opportunity to tell people about the center. Anyway, I thank also to my co-authors, Maria, who is here, and other people from UWA and around the world who have helped me put this talk together. So starting by the end, these are the 2 points or the key discussion items I would like to talk and engage with you this afternoon. The first one, I would like to try to convince you that understanding commonalities among diverse mineral systems, rather than focusing and emphasizing their differences, may actually enhance predictive targeting. So let's focus on how mineral systems actually share commonalities rather than always trying to box them as if they were part of something very diverse. The second one that I would like to convince you is that unveiling this cryptic DNA thread that may link the difference or the diverse mineral systems can actually help us open up search space for different ore deposits or systems in areas and domains of the lithosphere that we may have deemed as unprospective in the past, potentially for the wrong reasons. So these are the 2 key points for discussion, the commonalities and the search space. So in order to do that, as I said, I'm not going to talk about the Capval, but we do know that the Capval, potentially one of the most metallogenically endowed pieces of lithosphere on the planet, did actually experience a wide range of processes. And we know that the role of the cratonic architecture and of the lithospheric mantle in playing this first order control on its endowment. In the literature, we know that the geometry, the size of cratonic blocks really influence, from a physical point of view, the impingement of mantle-derived magmas and focuses a number of mineral systems at the edge of the craton. And in the Capval craton, we do know that those mechanisms may have played a role in metasomatizing the lithosphere and in potentially identifying and focusing areas where a diverse range of mineral systems may have occurred. And over the past 2 weeks in your beautiful country, my students and I have been really in awe of the beauty of the local geology, and we have tried to piece different pieces of the story together over a few billion years. But as I said at the beginning, I'm not going to focus necessarily on the capital Craton, but I'm going to take you for a ride on the other side of the ocean to Little Joburg. Yes, there are so many South Africans in Perth that it's known as Little Joburg. And actually, the Ilgan Craton, this is the Craton I'm going to tell you about, happened not to be too far away from the capital Craton about 2 billion years ago. We all know about what happened, about the 4 ancient cratons in the Paleoproterozoic, in the Paleo and Mesoproterozoic. And a few years ago, we put forward the hypothesis that some of the carbonatites in Western Australia may actually reflect the far-field influence of the bushveld. In fact, most of the large rare earth element deposits in Western Australia are exactly the same of the same age of the bushveld, 2.06. So, but regardless that, I'm going to take you for a ride over to the Ilgan Craton. And this is what it looks like. It's also a very metallogenically endowed craton. It's actually comprising a series of domains, a series of terranes that are largely comprising greenstones and a wide range of TTG granitoids. You may be familiar with some of the geology here on the left. And on the right, I put some of the mineral occurrences that have been defined. Maybe I should have chosen a bigger picture with that, but at least you can recognize the colors. We have in red the komatiite-hosted nickel sulfide systems. And for the ones who are familiar with the Kalgoorlie greenstone belt, with the Kalgoorlie terrane, with the Kambalda komatiites, we have in yellow all the gold system, the orogenic gold systems, and the large part of the story is going to focus on these orogenic gold systems. And then we have a series of iron deposits, especially in the central part of the craton, in the U&Me terrane. We do know, and we actually have mapped, and we have used isotope geochemistry to define the evolving architecture, and we've defined the presence of a very old proto-craton outside which a series of terranes have accreted or have formed. There is an evolving story, there is an ongoing story. I want to delve into this, but the point is that this evolving architecture has played a fundamental role in focusing komatiite magmatism in different parts of the craton at different times. Once we know that, as I said, I'm going to focus on the orogenic systems that are potentially, the Ilgan Craton is known for its gold abundance. You may be familiar with the super pit in Kalgoorlie and with the wide abundance of orogenic gold systems in the eastern part of the craton. And I put here a map, an isotopic map, specifically neodymium map, that provides us with a snapshot of the Ilgan Craton at about 2.65, 2.7, which is the age at which these orogenic systems formed. And actually, I put here on the right a recent complication, a recent compilation by Sumail and co-workers into 2024 that really has identified the age of gold formation, identifying different pulses, but really emphasizing maybe the most important one at about 2.65. So remember this age, 2.65. Gold that really aligns along this major lithospheric boundary that really is emphasized by the changes in the neodymium signature of the crust at that time, with an older part to the left and a more juvenile part to the east. Once we know that, you may be familiar with the work. I chose Groves et al. 2020, but the idea of how orogenic gold systems formed has kept petrologists and economic geologists busy for many, many years, and I shouldn't emphasize this enough because we are sitting on the Witwatersrand. So the gold controversies are actually what keeps us employed and interested over time. But basically, we do know that these orogenic systems in the eastern goldfields of the Ilgan Craton were most likely formed during a series of orogenic processes, drawing their metals and ligands from deeper in the crust and in the upper mantle. So why am I telling you all that? I'm telling you all that because for a number of years, we have characterized the nature of these orogenic systems. And we do know that they were in place at 2.65, as I just told you. And we have characterized very nicely now, if I say so, I'm a bit biased because I've been involved in this work, but we have used mass-independent sulfur isotope fractionation or signatures to really fingerprint the source of these sulfur-bearing and gold-bearing fluids, okay? And what we found out, maybe just on the left here, you see a little bit of a reminder about these sulfur isotopes. And I just remind you that sulfur occurs in nature with 4 stable isotopes. And usually, these isotopes fractionate from each other on a mass-dependent fashion. However, in the Archean, which is when our gold systems were forming, there was no ozone layers, and the sulfur, the gas by magnetic activity in the Archean atmosphere, had the chance to fractionate in a non-mass dependent fractionation way, simply because the UV rays, cosmic rays were interacting with these sulfur isotopes and fractionate in a funny way. Take-home message from this, from the cartoon on the left, is that in the Archean, we generated specific domains, the specific sulfur reservoirs that can be mapped simply because they had an anomalous sulfur isotope signature, okay? That I will be referring it as MIF positive or MIF negative, okay? We can talk more about that later if you're interested in this. What we found out about the sulfur contained in this orogenic system is that they are all MIF positive, but very close to 0. So they are just like mantle sulfur, but not quite, a little bit positive. You know, like when they do blood, 0 positive, that's the way I saw it, just a little bit positive, okay? But not as positive as the sulfur contained in the country rocks that surround these gold deposits, okay? Pointing to the fact that the source of the sulfur in orogenic systems comes from below, from reservoirs that sits either at the base of the crust or in the mantle. So time and sulfur. These orogenic systems are also characterized by the fact that they are spatially and most likely genetically associated with hydrous magmas, hydrous alkaline magmas, sanukitoids or lamprophires, without dwelling into too much details. And Smith et al. Over the past few years have really focused on this association. And last, I'm telling you 4 points to keep in mind: the age, the fact that there is that sulfur 0 plus or MIF plus signature, the fact that there are the hydrous magmas, hydrous alkaline magmas, and last but not least, this association with tellurides, with tellurium. The super pit in Kalgoorlie could easily be a tellurium mine, okay? A lot of tellurium associated as a semi-metal that is generally associated with the gold. I'm oversimplifying here, but I want to take you with me over a bit of a journey to try and get that point of the continuum. So what is happening on the other side of the craton, okay? So far, I told you the story about this orogenic system sitting in this Kalgoorlie terrain. And I mean, gold systems are across the entire eastern goldfield terrains and across in the specific areas of the craton. But for the specific purpose of the discussion today, we were focusing here. I'm going to take you about 600 kilometers to the west, just in the outskirts, about the broader outskirts of Perth. And there was a COVID discovery. People didn't have much to do during the COVID years. They decided to explore very close to Perth, and they found a layered intrusion, okay? So I would like to emphasize here this is not 400 kilometers like the Bushveld, but it's 400 meters. So it's a mini layered intrusion, okay? But it's a beautifully preserved one, okay? You may have heard of the Gonville-Julimar intrusion. This is run by Chalice, and I'd like to acknowledge Chalice for having a PhD project here, and this is actually the PhD project of Matthew Demmer, who is doing a fantastic work on this. So he characterized these intrusions that basically crystallizes towards the top and the left, towards the northwest. So you have the more ultramafic magmas at the base here, and the more evolved at the top there. And these layered intrusions contain an important PGE resource that is dominantly palladium resource, to the extent that the mine is going to be built in the next future. What does this, originally we thought when it was first discovered that there was some sort of association with comatiates, but nothing works for that association. And we have come to the conclusion that that had nothing to do with a comatiate-hosted system. So what is it? This is actually comprising a series of ultramafic serpentinites, orthopyroxenite, leucogabbros, and recent work from the geological surveys showed that the age is actually coeval with some of those orogenic gold systems that I was telling you about happening at the same time, 500 kilometers to the east. These basically PGE-rich magmatic sulfide deposit contains an extreme association with tellurites. So most of the PGEs are associated with tellurites, and nothing wrong. I mean, we do know that PGEs love tellurium, but the work that Matthew showed is that that association is overwhelming, and that 90% of the entire metallogenic budget is associated with tellurites. And also this intrusion is actually spatially and most likely genetically associated with a series of sanucitoid-like features that are actually outcropping within and beside the intrusion. These are on the right. Here is a nicely shaped PGM that Matthew has been documenting in detail. From a point of view of the sulfur isotopes, you can clearly see that I'm taking you the same lines of evidence I used for the gold. You would be amazed, but to see that the sulfur isotope budget here in red to the left is actually higher and different from the sulfur isotope signature that characterizes the country rocks, and pointing it to some sort of mixing between a mantle and the source potentially sitting there that could be familiar to, or could be similar to the type of sulfur that we thought or we think characterizes the orogenic gold systems. You can actually see on the right a comparison between the gold and the red, the Gonville stuff. So the work that Matthew is unveiling and I'm reporting to you here is that pointing to some larger scale commonality between orogenic gold systems that are historically have been documented from an hydrothermal perspective, and something that really looks like an orthomagmatic system, the Gonville-Julimar system. And the work that Matthew is basically working on is really looking at the potential presence of a fertile upper mantle that was able to feed the gold, or the deep reservoirs of the gold and of the PGEs at two ends or two parts of the craton. So the point here, the broader picture here, points to some of the work that I carried out with Dave Olwell at Leicester, and I'll tell you more a little bit in a few minutes about that ongoing work. But that points to the unveiling of that spatial relationship between the metasomatism that occurs in the mantle and the diverse range of magmatic hydrothermal systems. And the work that we published in Nature Communication a few years ago really aims at the linking. In that case, it was actually vertically, potentially looking at orthomagmatic system and hydrothermal systems as part of a continuum across the lithosphere. what we're trying to do now is really to explore the 3-dimension and linking different mineral systems across different parts of the cratons. And tellurium, we've seen tellurium, carbon, and the range of other metals and semi-metals are helping along the way to really create that unified picture. And we're not doing that simply because we like joining bits and pieces of the puzzle, but because we do think, going back to the premise of the talk at the beginning, that this exercise may help us think differently about the setting, the geodynamics, the location of different mineral systems, to the extent that Chalice is now exploring for PGE systems in the Kalgoorlie terrain, where people have really historically never seen the need. That has taken us to revisit the mantle sources for magmatic sulfide systems. And in this case, this is work in collaboration with the CMET 4D group that Dave and I and a number of collaborators have recently completed with PHP, looking at how different metasomatized domains within the mantle can actually yield and control the melting behavior and the metallogenic budget of a wide range of mantle-derived melts. We do all know that mantle peridot pyroxenites, and especially hydrous pyroxenites, melt at lower temperature than peridotite. That goes without saying. But what we didn't understand, what we hadn't appreciated, is the fact that the pyroxenite may actually contribute quite significantly to the metal budget of these mantle-derived magmas. Still, as part of this project with BHP, we have looked at how that source variability impacts on melt volumes and composition. And that's really important because that really painting a picture whereby it's not only about sourcing your metals from a specific mineral in the mantle, but by looking at holistically at how that metasomatic process, which in the past has been deemed to be significant for kimberlites and other type of mineral systems, this is key now for potentially orthomagmatic systems. Isra is a postdoc, staff at UWA, has also looked at revisiting processes whereby how metals can be extracted from the mantle, okay? Highlighting potentially the role of incipient carbonate melts at lixiviating metals from the source. And the work of Marias, who is here with us, has really taken that work further. It actually was the first to identify the role of carbonate melts in physically entraining metal sourced from the budget and transported them up through the lithosphere. So you can say that the thread here is about thinking laterally about processes that may actually link mineral systems that have historically been looked at as very diverse in nature. Okay, and specifically, Maria is looking at the potential for this carbonate melt to actually act as real drivers for copper systems and for precious metal systems. So looking different because historically, especially in Western Australia, carbonate melts are generally specifically looked at for their rare earth elements or niobium content. So how can we think about this system differently, and how can we make use of a wide range of new fingerprinting tools that may come available? I put here tellurium and carbon, but I've seen your fantastic setup downstairs. We can actually develop and new techniques and can unveil different fingerprinting agents all the time. So the work I wanted to tell you in a few minutes also more about this work that we have completed with Dave Holwell at Leicester in the PHP project, starting from the understanding that diverse mantle reservoirs may actually yield different type of melts with different volumes, different compositions. We went around and we actually fingerprinted these different potential sources and mantle-derived magmas across the globe. And we have identified these 6 end member types, okay, that actually display very different pressures. Probably you can see we have nickel, copper at the left end of the diagram. We have the precious elements in the middle to the right, and we have actually tellurium to the far right. What you can see at the, and again, this work is in reviewing economic geology, you can see a different shape for some of these features. Again, we can talk more if you're interested into this, but what we took from this work is that we have noticed that these different families or end member composition of mineralized magmas, from the ones that are more PG rich to the ones that are more base metal rich, from the ones that have nickel copper ratios that are pretty high to the ones that are predominantly copper rich. We have ordered them temporarily and identifying some very interesting secular trends in the abundance and basically setting of these systems. We came up then with a new way of looking at orthomagmatic systems that really not only stems from the idea that they are all derived from high degrees partial melting of a single source, but really takes in consideration that different mantle domains with different metallogenic budgets and different physical properties that may contribute to their partial melting behavior may all play a role in generating a wide range of different orthomagmatic systems. And again, why am I telling you all that? I'm telling you that because that speaks to that second point I was telling you about at the beginning, that search space. It's through this exercise that we have opened up a series of new metallogenic belts that may be prospective for orthomagmatic system in places where actually people have thought no chance could be there because there was no evidence of plume impingement or the MgO content of the magmas there was not high enough. Again, this is actually work that BHP is taking on in their exploration and the global exploration, and that could be of interest for the future. So in order to open up search space, I'm reading here, but you can read it by yourself. For this magmatic, I'm talking specifically about magmatic mineral systems. We talked about Julimar first, but we are broadening to the wide range of orthomagmatic systems that we may be familiar with. And if we really want to become more predictive in exploration of these systems, again, the narrative here that I'm trying to convey is that we should focus on the commonalities among these different systems without trying to box them into categories that actually are not talking to each other. So this is all work that I've been told half an hour, so I'm trying to stick. I mean, I'm Italian, so I can't be on time. I'll be just fashionably late, a couple of minutes late, which is what helps. So this is work that we are doing in this new center. This is a new center that it's transdisciplinary, not only interdisciplinary, transdisciplinary in nature, and aims to act as a boundary spanner between academia, government, and industry. And that's reflected in our sponsors and in the wide range of academic institutions that are involved in the center. The whole point here is looking at, I mean, when we first pitched this idea to the Australian Research Council, was not to really yet create a new center for a specific commodity. As we know that criticality changes every single month, okay? What is critical today may not be critical in 2026. Here, the point of critical resources really hinges on the geoscientists of the future. These are the critical resources we desperately need to address the challenges that are upon us, okay? And the way we try to design the projects that are part of the center is looking at ways to link data sets and knowledge across the value chain, to the extent that work done at the exploration end of the value chain could actually inform all parts of the value chain, all the way to processing and metallurgy. Nothing new till here, but what about if we put the metallurgist and we get their knowledge and their know-how, and we have them help us explore in a more efficient way, okay? How can we close that circle? Not only in one way, but in both ways, okay? So we want to promote the training for geoscientists that are more resilient and they are more knowledgeable about their value in the value chain, so that they can understand how data, which are very often currently used as a disposable good. You know, you use your data once and you forget about it. What about if we actually can gather information, extract information from data all across the value chain, and use actually data and interrogate data in new and fantastic ways? So these are the center stakeholders that have contributed to the center. And this is the 4 key points that I will read you. Well, I won't read you. You can actually, I can leave it behind, and that's it. Thank you. And now I need it. No, you can't. Okay, yet.
Let's try to see if there is a microphone. Maybe you have to come here. The microphone doesn't work.
Okay,
Okay, thanks a lot for fantastic talk. Just one very simple question. You talk about fertility, and there is another thing. So you have a certain type of melt which forms the intrusion, and this interplay between the fertility of the melt and the processes which happen within the intrusion. You can have fertile magma, but not enough processes to form. Just like in a very quick way, like what percentage of importance do you put on fertility of the source, or like the exact processes which happen? Because one example is, you know, like Norilsk, you have this huge Siberian traps.
An example by a really, just an example that comes to mind.
1.5 square kilometers. And in the corner, you have, you know, like these small intrusions. So it looks like in this case, fertility is not the main factor, but the exact processes are.
Yeah.
So, yeah.
No, that's a fantastic question. Thank you for that. I think that process, source, they are equally important, and it's when all things align that the giant systems like Norilsk can happen. I do think that source plays an important role also in Norilsk. However, that component, that role is potentially overwhelmed, overshadowed by a series of processes that have worked perfectly in the intrusion there and then. So I don't think, I mean, very often in geoscience, we tend to polarize the discussion, you know, like wet komatiites versus dry komatiites. Everything seems to be, I think both can, and it's fantastic when they think they both operate. If you have a fantastic source, but the processes don't occur in the right order at the right time, it's you're not going to form a good system. Similarly, if you have a fantastic process and everything happens during emplacement decrystallization in the right order, but you start with not a very good source, I would argue that you may end up forming a dull deposit, maybe sometimes a bit better, but we want in the future to find the big system, because we want to find the systems that are gonna, you know, be in place for a long time. So maybe the community should actually come together and talk about how fertility can marry process in the best possible way. But it's a very good point. Here I was emphasizing the source aspect, but process aspect are equally important, and for sure. Yeah.
Sorry, I can't speak to the.
Yeah, I can. Yeah. Yeah.
So go back to the beginning of your talk. You had
Okay.
gold.
Yeah.
You had nickel and all that kind of math stuff in the west. And to me, what's going on here is that in the east you have gold. We talk about orogenic. It's a crustal system. This is granitic system. But in the west, you have a little layered intrusion. That is a mantle rod system. And you're looking at commonalities between the two. You have telluride and mantle rocks. So how can they relate to each other? I think the answer, to me, is kind of obvious. It's impossible in my mind to find a layered intrusion, little one or big one, anywhere in the solar system, anywhere in our that doesn't interact with each other. So, what your little layered intrusion is doing is eating up the same kind of materials that are forming the granitic system to the east. So you have, and so what I would like to do is model the interaction between the systems, either in terms of their sources. It's always hard to get the sources, but the end products are easier to do, and you can do that. Neodymium, concrete, sulfur.
Yeah. Thank you for that point. So shall I just quickly repeat it?
Yes, they cannot hear, so maybe you have to repeat it shortly, Marco. Although it was a long comment, but maybe you can summarize.
So the question was about maybe an easier way to understand that commonality I'm talking about without really necessarily going to the source. It's actually about understanding the crustal processes. Maybe I butchered the question a little bit, but that's in essence. So the point I didn't make maybe strongly enough is that in the West here, we have never found a layered intrusion before. So the others, there are a few gold systems. You may be familiar with Boddington, which is probably one of the largest gold systems in Australia, which is a bit later. It's a bit older, 2.7. It's more or less the same age of the Komatiites. So this layered intrusion is actually a bit of a novelty. That's never been identified before. And the key thing that probably didn't come across from my talk is that all isotopic and geochemical features that characterize these layered intrusions point to actually a lack of interaction with the surrounding country rocks. There is no evidence of a sulfur input from the country rocks. And from a radiogenic isotope point of view, there is no evidence that these magmas interacted with the country rocks. Let's see. Maybe there is the.
But they are asking about the epsilon neodymium of these rocks.
The epsilon neodymium. So these basically are sourcing stuff that is, the country rocks are old. They are basically in the minus 3.54 range. And the stuff that we are looking at is much more juvenile. Pointing again to a nature that is not known there. So again, I'm not trying to dispel this is a working hypothesis, and certainly it's based on a single occurrence, which is this layered intrusion. So it's more of a thinking exercise rather than anything else. Yeah.
Your layered intrusion has not interacted with the crust. If that's the case, it's the only one that we know of on the planet. The more likely it has interacted with the crust. And what is very difficult problem in petrology is to distinguish that isotope signature of contamination of crust
Yeah.
from the source,
Yeah.
from an enriched source. Almost impossible to understand.
The question is how difficult it is to separate and to discriminate signatures associated with crustal assimilation to potentially signature associated with the involvement of an enriched reservoir, deep reservoir. I would like to address that by saying that I'm not, I mean, a hot magma intruding a felsic crust. There is no doubt that interaction occurs. The point that I'm making is that interaction leading to the ore forming process? That's where I'm arguing, because the evidence that we see from multiple sulfur isotopes is that you basically, maybe this is a type of data set that is not very familiar, but when you are basically interacting, when you have in an Archean system and you have a magma being intruded in the crust and you have sulfur reservoirs that sit at this level and you put stuff that is farther away from the mantle signature than the country rocks, you need, by basically necessity to imply that the magma has interacted with a reservoir that is not present in your country rocks. I think there is a Nick Arndt question, and I'm already worried because I mentioned the wet comatiates, dry comatiates here. Maybe, Nick, would you like to? I know, I'm joking.
Nick Arndt. He's going to ask a question.
Ask to unmute. You would like to unmute, Nick?
Okay,
Yeah.
now is it okay? Can you hear me now? I'm talking.
Yes, we can hear you.
Whoa.
You have to be a little bit louder, but we hear you, Nick.
Okay, so Marco, an interesting talk as always. You know, I'm just going to focus in on the.
Coming, isn't there?
No, the but comes. Of course, the but comes. Fertility. And you talked about magmatic system. I'm thinking out loud here, but really, if you talk about the nickel systems, it's an argument against a fertility control, because if you consider them from komatiites through Norilsk through to Sudbury, you know, you're getting magmas which are very different, which have very different nickel deposits. And as you know, as Tony Nolder has said all the time, there, when you talk about the magmatic nickel sulfides, it seems the process is far more important. I'm looking at what you said, and surely you seem to have good evidence here in the slide I'm looking at that the sulfur doesn't come from the immediately adjacent country rocks, but there's always a problem that we don't know what the rocks are in the 30 or so kilometers of crust that the magma penetrated on the way to the surface. So really, you know, you have some good ideas, and I'm trying to think them through, but yeah. So no real question, just a rather confused comment, I'm afraid.
We are building that reservoir. I mean, the MIF sulfur, as you know, is really relatively in its infancy. I'm showing here just the gold values, but there is a growing data set on the sulfur isotope signature of Archean greenstone hosted sediments, and that really points to a great variability all over the place. The point here that I'm trying to make is that usually when we find the sulfur isotopes of these systems, they're always very punctual, they're over clustering at one point, and they're just at odds with the local stratigraphy. So
sure, yeah.
I take your point that signature could be just sitting underneath. However, as a thinking exercise, and taking into consideration that we are building these connections, I'd really like to push maybe that connection further down and use that even just from an empirical standpoint as a guide to really drive exploration and open up areas that may have not been considered before. So PG systems in the eastern goldfields, for example.
Yeah. So, for example, in Jinchuan in China, it's a nice big deposit, and the country rocks are conspicuously poor in sulfur. So there must be different mechanisms to lead the sulfur to segregate from the magma, and if that sulfide can then accumulate, you form the deposit. So, Ben, just to repeat my first statement, in the case of nickel, the fertility argument doesn't really apply.
I hope you haven't, you're not reviewing our paper there, but in case it gets accepted,
You probably said don't send it to me as one of the unwanted reviewers.
You know, I don't know, but in case it comes up, I'll send it.
In case.
Once it's published.
Okay. Anyway.
Bye, Nick.
Interesting talk. Thanks, Marco.
I think I thank Marco and I thank all the audience for being here. And I thank you for visiting us at Wits. And
thank you for your hospitality. It's been fantastic.
It's nice. Maybe there is a way for us to, through this center, actually to start also to work together. So we are also making a new reviving of the old agri here at Wits. And so I think there is a vibrant new group of team economic geologists at Wits. And so it's nice that we could maybe join together in effort.
Actually, we have some of the students are part of the student chapter of the economics geology at UWA. So maybe you could actually make
exactly, because there is also here Carol, that is the president of our economic Sussex, the student chapter of the CG. So there is many different ways that actually we could start to stay in touch in a constructive way. Thank you, Marco. Thank you, everybody.
Thank you all for coming along.
And thank you. Bye-bye.